very. Okay, well, good afternoon, everyone. Thank you for joining us today. I'm going to just be giving you a couple of minutes to introduce Urban Institute and my team member who's going to be presenting today. My name is Khulud Ode. I'm VP and CIO at the Urban Institute, and we are a think tank and research institute based in Washington, D.C. Our mission is really to open minds and shape decisions. So we work on social and economic policies in the US. We have about 9 or 10 policy centers focused on different areas, from justice policy to income and benefit, health, justice, and tax policy, and way more. So if you follow up on what's happening with the tax or with changes in policy, I'm pretty sure you will find Urban name or a number of research over the years that contribute to some of those. Most of our work is really all data-driven. So Urban, half of the staff that I work with is really economists, and it's always wonderful to be in a place where people are so smart around you. They're all driven by data and evidence, and that's the reason they come to work every day. And as an IT leader, I find it challenging, but at the same time exciting to have such smart people around me all the time. They always drive me to the edge, trying to really bring more capacity and more technology for them to do their work. Urban Institute, like any other organization, we are a nonprofit, bipartisan research institute, and like many others, our focus is really always on growth in the areas we work in. So these are kind of our 4 pillars or 4 strategic objectives as an organization. Is we want to grow in everything. We want to grow the type of research we do, the quality of research. We want to grow our visibility and impact. We want to make bigger difference in the life of communities that we help drive policies that serve them. And we also want to expand our funding so we can do more research. And of course, we want to expand our capacity in operating and the infrastructure we provide for the organization to function. So with that, 2 years ago, when I joined Urban Institute, I was faced with a typical challenge that an organization that underinvested in technology for a long time is faced with, which is you basically want to modernize everything. And you feel you're missing opportunities, especially in the areas of data analytics and research technology, which is the core of what Urban does. Urban has a number of flagship products. We call them microsimulation models. And they are fascinating in what they do in terms of informing policies. Some of these models, they really take 500 variables in some cases and analyze different scenarios. What will happen if we change this aspect of the tax policy? What impact would it have on a single mother? What it would have on you, or if you have kids, if you go to college? So it's fascinating. Every time I learn about how these models work, I really get thinking of, okay, what will happen if we really enable our researchers to be able to do more, or to run some of these models instead of running them, for example, for one state? How can we run all the models for 50 states at once? And traditionally, urban technology has been all built in-house. And I have a few members of my team who actually participated in building this infrastructure and great technology platform for our researchers over the years. But with the growth of data and analytics and big data, it has been a challenge to keep up with capabilities to really analyze and work on those data. So I'm not going to share with you what we did on the infrastructure side or the user technology, but mainly the main thing we really turned to was really the cloud. Not because it's the hottest thing, but because it's the type of technology and architecture that suits what we needed to do, which is a big transformation in moving our capacity and focus the skills we have on really to do what matters most. So a couple of things we started with, and I'm just sharing the parts we did and the core, which is the research areas. We started with our publications management and our website. We built our capacity to do data visualization, so I encourage all of you to visit our website and see the type of interactive data visualization that we do to really tell better story with the data and research we do. For example, our website and publication management, that was the reason I mentioned it here, it's because it was our first exposure to leveraging AWS. We moved the publication management system in AWS, and that was our first really encounter to see really the power of having a scalable and elastic architecture. So we connected our publication management from AWS to our new Drupal website. But also we kept experimenting with more things to do with AWS, and we tried to move some of our modeling to the cloud, and we came up with a number of architecture of how we can run these models in parallel, how we can run them on Hadoop, and we are still continuing to really move this more into production, and working with our AWS professional services and partners to really make this happen for our researchers. For that, I'm going to stop and I'm going to turn it to my colleague, Alex Engler, who will share with you one experiment we've been doing in how we want to analyze big data. Thank you.
Thanks, Lud. Hey, everybody. I'm Alex. So just a couple things, just to really quickly build on what Lud said. I'll get to that in a sec, but it's awesome getting to work at the Urban Institute. The Urban Institute has been a very data-driven social science and public policy research organization since it started. It was doing microsimulation models 40 so years ago. And that's been fantastic because there's already a large group of very data-oriented people who are amenable to sort of the new wave of data analysis that we're seeing today. And so some of the other things that we're doing that's not related, but it's just too cool not to mention, is we're writing natural language processing into some of our social science grants, machine learning for prediction of stuff like reincarceration. And a lot of what moving to the cloud and modernizing our systems lets us do is reverse the way in which policy questions are asked and answered. And this is a really important idea. If we can make everything we do run very, very, very quickly, then microsimulation models don't have to be a researcher runs a model, waits for several hours, then writes a report, and then 3 or 4 weeks later that report becomes public, and then we show, these are the results of what happens if we do this tax plan. It becomes much more about individuals come to us with questions, and they interact with a data tool that answers their policy questions right then and there. And that's definitely a shift we'd really like to engage in, and then requires a very modern data architecture. So this is sort of part of a bigger public policy and social science movement. I'm not going to talk about that too much because you guys may or may not care about that, so I'm going to talk about Spark instead. That's me. I'm Alex. I do 2 things. I work at the Urban Institute doing the stuff I was just telling you about. I also teach at Johns Hopkins and Georgetown in their public policy schools. So if you care about data skills and creating pipelines of social science and policy-oriented people who have strong data skills, please come talk to me. I love talking about it. If you're an employer and you are looking for people with skills and you're having trouble retaining them because they go work in Silicon Valley, maybe the solution is train policy students to do what you want them to do. So I'd love to talk to you about that. And I do have one disclaimer before I talk about our problem. I don't know if there have been a couple of presentations about Spark today. I don't know if you were paying attention for the scale of the data at the Fermi National Lab conversation or Johns Hopkins population scale genomics data. That is larger. That is a tougher problem than the problem we have. And so we're not going to get quite to that big data. Our big data is just not as scary or intense. Our problem and what we're really focused on is accessibility. And Spark is a game changer for how accessible big data analysis can be to individuals who are not part of organizations, who don't have operations teams, who don't necessarily have a staff backing them, who are just individual data analysis or, again, small organizations. And so Spark combined with EMR, which is what we're going to mostly talk about, the elastic MapReduce system, is fantastic for this. This is our big picture problem. We have what we in social science would call big data. This is like 700 million to the low billion number of rows with maybe 30, 40, 50 variables somewhere in there. So again, not the same scale as some of the other projects, but for us, it's big data, right? It no longer, when your SAS jobs are taking 20 hours to run, that's a problem for social scientists. So I'm going to talk about one that's mortgage data from our Housing Finance Policy Center, but administrative data is becoming an issue too. Very, very large data sets that are about interactions with people in government are becoming more important, and those are the types of data sets that will warrant, large, scalable statistical environments. 2, small budget. I mean, this is maybe the toughest one in a lot of ways. If you spend enough money, you can get lots of big data things, but we didn't have very much at all. We wanted to really make this as cheap as possible, and so elasticity was absolutely critical. We need to be able to spin up clusters, use them, and turn them off when we're not using them. Third and fourth problems are real too, though. We need advanced statistics. And this is why Spark makes such a difference. Back when we had MapReduce largely with Hive and Pig, it simply couldn't do the types of causal inference and social science methods that we needed to make judgments about policy. That changed a little bit with Mahout, which is a machine learning library for Hadoop, but Spark is still it's very good at interactive jobs, and that makes a big difference in this. I'll talk a little bit about why. And the fourth is that the programming limitations. So most Pig, even SQL, these are not tools that are accessible to social science researchers who are accustomed to Stata and SAS. So we needed to get as close to Stata and SAS as possible to make the lift in terms of dealing with data analysis as low as possible. Because, a lot of our researchers are very curious, engaged people, and they care about these tools, but they don't care about them more than they care about the social problems that they're trying to study. So every minute they can spend on policy research is better than a minute they are learning a tool. So we want to make it as approachable as possible. So our solution looks something like this. We did consider on-premise, but we are looking to move as an organization, and we didn't want to buy a new server and then have to move it in just a couple of years. We looked at a permanently standing cluster in the cloud, and then you're paying for EC2 instances 100% of the time. And that was, we were looking at that with high-performance SAS, and just the total amount of money between the SAS licensing and the EC2 was pretty brutal. On top of the fact that that's not elastic anymore, because again, the licensing for SAS is based on the number of nodes you use. So that we did consider other things, and sort of we landed at this combination of Spark, EMR, and Python and R in browser, and that middle one is going to be pretty important for our use case. So I'm sure you guys have heard some about Spark. If you don't know what it is, just a quick recap. It's a distributed memory framework, and this is not a replacement for Hadoop wholesale. It's just really a replacement for MapReduce, so it's the processing side of big data. It's not going to replace your storage system, whatever you're using, or your resource negotiator. But it's a really great tool for interactive data analysis. So the type of data analysis you most commonly see in social science and policy research is very exploratory. It's not batch jobs. It's not streaming data where something needs to happen all the time. The researcher is sitting in front of the computer, asking questions of data, wants to immediately see results, and then iterate on those questions. And so your ability to sit there and then just see the results of what you're running is really important. And again, when you get into these several hour, even several day runs, that becomes very hard. And it's particularly important to an organization where our largest expense by far is researcher time, right? The people who are sitting there doing the data analysis, that is by far the most important and most expensive part of a think tank. So other important, what else is, so Spark, the other issue, Scala and Java, that's what it's written in. These are not approachable languages for researchers, but hey, there's R and Python APIs. So Is that the same as SAS and Stata? No, but it's close enough that we're going to make do. And I'll show you guys a project a little bit later where we've started to make SparkR and PySpark as accessible as possible. We're doing that on public GitHub repositories that I will point out. The statistical methods are good, again, because it's this iterative, this interactive analysis. It's pretty good. The Mahout project has basically moved on to now working on MLlib. So all the people who were working in MapReduce before and have now focused on the Spark MLlib. So we have good statistical methods. They're still aimed more at data science problems, by which I mean, you know, we're getting like great versions of recurrent neural networks. Like they're fantastic and they're implemented at a very high quality, and like in public policy research we couldn't care less. It's like totally useless to us. So it'll be nice to see some more social science methods come out. We're seeing that a little bit. Cloudera's team just came out with a time series modeling package for parallelized ARIMO to time series modeling. And then there is the generalized linear model framework there as well, which we found we can actually get a lot of what we need out of just that. So it's not perfect there, but it's good enough for what we need, and we can reasonably expect, since it's open source, that it's going to continue getting better. And it's, you know, there's now, I think they just hit 1,000 contributors to Apache Spark last year, so presumably there's more than that at this point. So this is going to be our workhorse. But we don't want people to work in Scala, as I mentioned, and we don't necessarily want them working in the command line, because that's just, again, not, you know, public policy researchers very used to having a development environment like the ones that come with Stata and SAS. So even though Python and R are not the preferred, again, much closer than Scala, and so the other challenge we wanted to deal with is get an integrated development environment. And so what we managed to do is get RStudio, which is the most popular development environment for R, and Jupyter Notebooks to work in browser pointed at the cluster, and so researchers never have to work at the command line. In fact, they'll never see the command line in this entire process. Okay, and then we have EMR. This creates, and I think you've gotten a sense of this hopefully throughout the day, so I don't want to repeat too much from other people. This creates temporary, I like the word ephemeral, clusters. We're going to spin them up, we're going to use them again, usually when a researcher's sitting in front of it, interacting with it, and then we're going to shut them down when we're done. This is going to use S3 for storing data before and after, which is important and very critical that S3 file transfer to EMR and back is free. And it actually happens in a parallelized way as well. That itself is efficiently parallelized, and we've seen it happen pretty fast. And so what we're going to do is we're going to pull data into EMR. Every single time we want to do an analysis, we're going to do the analysis there, and then we're going to write it back to S3. And that comes with a little bit of overhead, right? Because we have to spin up the cluster, we have to install some stuff in the cluster, load in the data, and then save it to a different place. But when you look at how much this saves us in terms of cost, it's tremendous, and the relative amount of time that you lose is pretty minor. So that looks something like this. And this was a really great solution. I was really happy with this when I first figured out that it was doable, especially with how much progress is being made on PySpark and SparkR. And I had forgotten one little problem. So I could spin these clusters up personally, but no one could get to them. So my first attempt at fixing this was not great. It took a 4-hour setup time on someone else's computer. I had to sit down at their computer and create for them an AWS account, get them a key pair for EC2, install the Amazon Web Services command line, point that at a Linux file to Bootstrap, and the Bootstrap is going to install some stuff. I'll explain that in a second. Then I had to install PuTTY, because we have Windows computers, so everyone had used this program PuTTY to securely get into the foreign cluster. And then port forward your browser to the browser of the machine in order to see RStudio and Jupyter Notebooks. And so that ended up being like a 3 or 4 hour install process every time I wanted to give someone a cluster. And then you'd have to do that once and then not again. So thankfully, and I have some people at AWS to thank for this, there is a better way. I'm going to talk a little bit more about this, but this is not what we are advertising or expecting people to do. This is not what the GitHub page that explains how to set this up on your own asks you to do. We did, in this time, though, write a couple useful scripts, one for R and RStudio, the other for Python and Jupyter Notebooks. These are both public, and they do a couple really useful things. This is going to it's going to install R, which does not currently come on EMR. It's going to install some packages from R that we need, but anything that you want that you're going to use regularly, you could drop in. It's going to also give you RStudio and set RStudio pointing at a port. So RStudio is sort of waiting, and the second you try and get to it, the researcher won't have to do anything else. It'll just appear in browser. And we have a version of this for RStudio, and we have a version of this for IPython notebooks. And I will make that available if you want to look through it. It doesn't really matter if you can't see it right now. So this was really useful and automates a lot. It really removes the Linux command line from the role of the researcher, which is something we absolutely wanted to do. And so this is sort of what we thought it would look like later on, which is we do this installation, they'd launch a cluster from Amazon command line, and then they'd open a web browser and go to the cluster IP, and then using this Foxy proxy, which is port forwarding, they'd appear in the cluster. You do not want to do this part either. This is, again, the old system. And it was still good. It took about 15 minutes, but that setup time, it was 4 hours of setup on some. Every time a researcher wanted to do this, I would have to sit down for 4 hours and figure it out. And this is a Python script that's sort of running all this. It automated some of these processes and got some of the other way. And this, again, was the old method. What we replaced it with was CloudFormation, which we had no idea existed when we started this project. And I did not. It took me a little while to come around. But I want to thank Bob Strahan, who's right here, who may join us up here if you have any questions about it. But he pointed this out to us, and it completely replaced, so that underlying infrastructure of R and Python through IDEs in browser to Spark on EMR, that's all still there, but we changed how we spin that up and how we access it to remove all those local installations. And there are two important parts of the CloudFormation. The first is specifying of parameters. And this is security stuff, for instance. This is specifying an EC2 key, a VPC, this is a virtual private cloud, your subnet, allowable accessible IP addresses. Really important security stuff happens in here that I am not qualified to talk about. So hopefully you had a colleague go to the security portion of some of today's events, because I really shouldn't be answering those questions. But this is where you would do that. You can also do things like set the number of instances you can spin up and what type of instances. This prevents a researcher from accidentally asking for 200 nodes when you really only want to give them 20. So this is what the parameters section kind of looks like, and this is, again, setting some of those. And then there's the resources section of the CloudFormation, which is going to let you specifically ask for an EMR cluster. And also, it could set up security groups, which we have it doing here. And this is it referencing a Bootstrap script. In fact, you can see, mentioning Bob's Bootstrap script. And then some arguments it's passing through about what we want that script to install. This could also create buckets in S3, logs, stuff like that. But what's nice about this is that this gets you, I'm going to show you where this gets you in just a second, but this is going to pretty much obviate all of the setup for researchers. They will have to click a couple buttons in the AWS console and load that CloudFormation script, and they have to wait 15 minutes, and then they're going to be greeted by either SparkR in RStudio or PySpark in Jupyter Notebooks. So I'm going to talk about what this looks like in application and why this is so great for giving individuals access to cluster computing, which is really why this is such a powerful differentiator. So this is sort of this is the project that originated our need to deal with big data, but it also just fairly well exemplifies what a big data social science project looks like. We had 800 million rows or so of data. There was actually 2 data sets. There's another data set of like 20. There's really one of 200 million, one of 20 million that you start with, and then you build that into this much larger data set. And that's growing over time. So they need to run this analysis every few months, and every few months the data is getting bigger as well. This is data related to mortgages and mortgage default, which is sort of something that HFPC, our Housing Finance Policy Center, might classically study. So that's getting us somewhere towards a terabyte of data. Not exactly, but a terabyte was a good benchmark of that's what we want to be able to work with. And requires absolute minimum of some data manipulation. This is your classic social science filter, sort, aggregations, merging, the absolute core things you need to be able to do, as well as logistic regression. And so this was nice because it was, a causal social science method, but not one that was going to break the bank. We didn't have to do instrumental variables and then a multinomial, it was fairly straightforward, so it was sort of a good first project to bite our teeth into. And this was running on a on-premise SaaS server in somewhere between 15 and 20 hours, depending on how many other people were using the server at the time, which again, in terms of researcher time, can be very taxing. And now some other things would be nice, right? We want to be able to do data manipulation, data visualization, some other sort of add-ons, but this is what we absolutely needed. And this is what we ended up spinning up in the EMR cluster to do this. And this is 4 R3 8X larges. The 3 important numbers on here are you're getting 130 processors, give or take, a terabyte of distributed memory for $10 an hour. And being able to give this to a researcher who can then actually work in that environment is something you simply couldn't have done before the Spark project because of how powerful its APIs are, or before something like EMR. And so this is what happens when you actually, this is the first thing they would see after clicking a couple buttons in the AWS console. Looks pretty grained out, but this is our studio. It appears in browser. If you've ever seen our studio before, this is exactly the same. Code up here, sorry, no, it's really grainy. Code up here, runs down here, graph over there. Classic RStudio. And for those of you who haven't seen Spark code, it can be pretty straightforward. There is some complexity. Spark is not a simple tool, but the setup is 3 lines. Those top 3 lines are the only 3 you need to run. And we'd probably specify those to the cluster. And you would again run these when you get to RStudio. So that's the whole setup. And then the second set of lines here is reading in data. And this is functionally exactly the same as R. It's using read.df instead of read.csv. It's pointing at a location. In this case, it's pointing to S3. Again, that file transfer is going to be free to get it into EMR. It's saying there's not a header and that it's a column delineated file. And then it's showing that data. But this is almost exactly the same as reading in data in just base R. Similarly, for any of you familiar with dplyr, which is a really common and powerful data manipulation library in R, these functions, which is filtering, aggregation, and arrangement, are almost indistinguishable from normal R. And there's now reshaping to or pivoting, depending on what you're familiar with, available as well. And so you're running these commands like this, and you're getting 130 processors working in memory, in distributed memory, working in your data, which is, so not only is this understandable and accessible, and researchers are working in an environment they're familiar with, it's also just absurdly fast. And we even got, we want to do more of these. Data viz is not quite as straightforward. If you have 200 million rows and you ask a distributed memory system for a scatter plot, a couple things go wrong there. So data viz is a little more complicated. You have to run an aggregation first, and then bring that aggregation into the memory of your master node, and then you can plot it. And so that's what this looks like here. But first I'm just running an aggregation, just grabbing a count by a certain variable. I'm bringing it to the master node into memory. That's what the collect line is doing. And then I'm just running a normal plot on top of it and producing a histogram. So it's not exactly the same, but it's still pretty close. And then you have doing something like logistic regression or the generalized linear model. And this is again exactly the same, totally indistinguishable. This is an interesting area that we as social scientists care about quite a bit. We really, the methods available to social science researchers and the ones we need are not the high priority ones for Silicon Valley and the West Coast, where most of the really talented Scala developers are, and that's where the money is. So we do know it's going to take some tricks and some time for all of the models that we really care about to become present. But what we've learned just by sort of thinking through this is that the number of models you can fit into this framework is actually pretty high. So things we really care about, like difference in difference, fixed effects, multinomial logit, all of this can work within just the GLM command if we specify models correctly. And again, we're just also banking on the development of one of the most popular open source projects in the world, that it's going to become far more powerful, and the people who really care about this, like you saw earlier for energy or Fermi or at genomics, are going to build new methods, and social scientists who don't necessarily have that overlap of skills will benefit from it. And that's what's happened in languages in the past, and we're sort of have our fingers crossed. And survival models is a good one. We know, for instance, that people have requested on Spark for survival models to be built, and that the Spark developers said, oh yeah, sure, we'll get on it. So, some of this stuff we can sort of watch as it's happening through the GitHub pages. So we did run some speed comparisons, and this was not the largest. This was around an 180 gig file, I think, and then we merged it with like a 15 gig file. So this is double digit, in the hundreds of millions of rows at the end. So after that merge is in the hundreds of million rows at the end. So not the largest data we've put in there so far, but this is what we had comparable to other systems. And it's important to note that the speed comparisons are not comparing the same thing. One is SAS running on our server when possibly other people were using it. Two is high performance SAS, and so this is what we were trying to get to. We were trying to get an open source elastic solution that got, that was much cheaper, but got us the same speeds as parallelized SAS on a cluster. And that was on a Cloudera Hadoop standing cluster, and it was optimized by the SAS professionals, which I do think probably gives it a bit of an edge. And then it's just comparing it to SparkR on EMR, kind of optimized by me, because I'm still figuring out what that process really entails. So pseudo-optimized, I would say, is fair. Now, for the record, this is the AWS brand table. So the text, the white, that's not, I don't want to take the blame for that one. All right, the first row is SAS on a server, the second row is high performance SAS, and the third row is EMR and Spark. And then we have a couple tasks, so you can, you compare up down for the same task. The first one is just a data import. The second is a sort. The third is a merge. The fourth is a simple aggregation. And the fourth is that logistic regression. And we found ourselves matching and beating high performance SAS on everything, except for some of the aggregations, and that has to do with the way that high performance SAS saves schemas in a very efficient way. So it can do certain aggregations very, very fast, because it's got a particularly adept look at like frequency tables, for instance. It knows people are going to do a lot, and so it saves in the schema certain ways to do that faster. But we overall, and by the way, they created that schema at the data import, which is why their data import takes so much longer. But overall, we beat the benchmarks that we set out to beat, or at least got very, very close. So just to sum up, this is pretty much the last thing I got. We needed something that met what, the timing's sort of fortuitous. If we had this problem, and we had been presented with this problem 3 years ago, we would have been looking for a bunch of things that didn't really exist yet. And so the ability to do all this in one system is really fantastic. And the last thing we're going to do in a slide or two is I'm going to show you guys where you can go and find step-by-step instructions to set a lot of this up. But just in terms of what this did for us, it's totally scalable. What I showed you was 1 terabyte of distributed memory with 130 processors for $10 an hour. There's no reason that couldn't be 2 terabytes of memory with 260 processors for $20 an hour. It scales perfectly linearly. Now, the speed probably won't. There's different considerations there, but it'll handle more data and it will get faster as you pay what it seems to us is fairly negligible amounts of money. So again, that's your scalable and your low cost. It's fast enough that, you know, when you're looking at these times, the fact that a 200 million row data set merged to a 20 million row data set takes 2 minutes is pretty interactive, right? That is efficient to the point where a researcher can sit there and it relatively interactively work with large data sets. And again, I don't think we've totally perfectly optimized this, but this really does solve that issue that it needs to be fast enough for people to work interactively. Elastic, I think I mentioned a couple times. I'm sure you've heard this word a billion times today. We can turn it off when we're not using it. And again, it's accessible. You're going to get to it R and Python and browser with those integrated development environments that make it approachable. And we talked about the statistics as well. So I have a couple thanks real quick. He's not here, but I am like a data science-y person, I guess. We have a systems engineer without which this never would have happened. So if you ever run into a guy named Emmanuel Davina, he's like half the reason any of this work was possible. Sadly, he couldn't make it today and to take any credit from me. I also want to mention, Khulud, who spoke at the beginning, is the reason that we can do this is because it's an investment in tech and in cloud such that we can be a very forward-looking social science organization. And I'm fairly certain that we're the only people doing this really in our field. And so I feel really privileged to work at a place that's investing in that. So thank you to Khulud and Doug Murray. And also, I don't know if they're here, but we have 2 people joining us for the summer, Sarah Armstrong and Jeff Levy, who are writing code tutorials in Spark R and PySpark, and they will be available on our public GitHub, which is Urban Institute. And I'll show you guys that in a sec. Then there's also the AWS people that helped. Rahul Pathak who is the head of EMR business, wrote several pieces of code that made this all much better. They were great. I think I just tweeted at them and they started tweeting back and eventually wrote code for us. And so that was really honestly great and totally unnecessary. So we really appreciate the EMR team. And then the big data services team, which is Bob and Malini, who are sitting right up here, have been wonderful as well, and especially applying CloudFormation to our problems. So the last thing I want to do, T, could I bother you to click on the link? Thank you. T is our wonderful AV assistant in the back today. Or yeah, if the link's not going to work, going to the... This is Spark Social Science. This is a GitHub repository on Urban Institute's public GitHub. If you can scroll down a little bit, there's a security disclaimer. But this repository has Bootstrap scripts for R&R Studio and Python and Jupyter Notebooks. It has CloudFormation logs, templates, to do either one of those things, and step-by-step instructions on how you need to fill them out to get them to work. If you are using non-private data, right, so using public data, and you don't need to worry seriously about the security concerns, and you're an individual and you want to do big data analysis, this will get you there in like 20 minutes or a half hour. And that's as easy as I can possibly make it. We will be monitoring and updating this. We're, again, trying to make this something that's externally facing and helpful to social scientists. And then at the T, if you could go back up for me. Thank you. That's perfect. There's also 2 links to Spark R and PySpark tutorials. And they are new. We started those repos a couple weeks ago, but we have 2 people dedicated to working on them through the summer, and we're trying to cover as many of the social science methods we can in R and Python in understandable code. And the documentation for Spark is iffy at times. So we're trying to make it as approachable as possible for non-technical people to do big data analysis. So with that, thanks for your time, guys. I hope that was helpful. And I'm going to stick around and answer some questions, I think. Also, you could leave, too, because the conference is, like, over. It's like 4:30, right?